Giovanna Carnovale will tell us about enhanced and exotic module. So yes, you have until a bit more than a minute.
Yeah, you warned me. Okay, so I thank the organizer for the invitation, and so what I'm going to talk about is unfortunately pretty much in progress. So, but it was the closest thing I had to talk about to symplectic singularities, and say I guess that if we met in a year, this talk would be more complete. But, okay. This is it. It's joint work with several people who are interested on different aspects, and so what I'm going to tell you is what are the enhanced and exotic modules. These are very apparently very innocent representations of GLN and of the symplectic group, but they have a lot of interesting properties that I want to promote, and I want to tell you what are the questions we are interested in. We don't have all the results we wanted, we just started, but okay, so let me start the discussion. So the enhanced module is a representation of GLN, and it's simply this representation. You take the adjoint representation, so GLN acting, the group GLN acting on its Lie algebra, but you add the standard representations of matrices on vectors. And so this is a GLN representation. And the exotic, on the other hand, is a representation of the symplectic group, and is the following. You take the standard representation of the symplectic group, you take the second exterior power, and you add, again, the standard representation. So this is vectors, and this is vectors again, and then again, two forms. Okay, and this is an SP2N module. Okay. So apparently they are very, very, very innocent, but they have occurred in many occasions. So probably the first appearance, the first study of this module was in the 80s by Bernstein. He was studying p-adic groups, representations of p-adic groups, and he was counting orbits of GLN and here. And then the first deep study of this module was by Kato in the beginning, in 2000, and he was interested in Springer theory. So he constructed, Springer theory is a paradigm that allows to attach to nilpotent orbits representations of the Lie group. So orbits of nilpotent elements in a semi-simple Lie algebra to representations of the Lie group. And in the case of the symplectic group, this is not really a bijection, but instead of taking the adjoint representation, you take this module, then you get a bijection. So yeah, and maybe you know more about it. K is just a field, and in fact, what is interesting for mathematicians is the fact that here you can take really any field of any characteristic. And if you're unhappy with this, probably for this talk it's enough to think about the complex numbers. But many things I will be telling are true, hold in general, or at most some things in odd characteristic or zero characteristic. But okay, and so this was studied by Cato, and they have been studied by several people. I will tell along the talk what these people have been doing, but for instance, Krapkin and Jan Ginsburg were studying this for studying geometric algebras. Then Achar and Henderson studied the relations between these two modules, and I will tell more about it. And Springer also. In fact, the results of Springer and Achar Henderson have a partial overlap, and also Bellamy and Bose describe the relation of this module with representations of cyclic quiver. So, I mean, they occur in many different instances. Okay, and what is, for instance, special about it? So, what is special about that? One thing that we can tell about both is that they fit into the framework of some representations that are called polar representations. They have been studied in the 80s by Dadok and Katz. So they are polar in the sense of Dadok and Katz. And what does it mean? Essentially, what it means is that I will not give the definition, but what is interesting about it is that you have a sort of Chevalier restriction theorem. So let me. So what does it mean? So what we know when we study matrices in linear algebra, what you may want to know is you want to know what are the regular functions that are invariant under GLN. And essentially what you find out is that these are just the coefficients of the characteristic polynomial. So you take the matrix, you take the characteristic polynomial, and you look at the coefficients. And so this is the same if you take a matrix or if you take just an upward triangular conjugate to them, right? So this means that in fact, this is just the same as taking diagonal matrices under the action of the symmetric group. Okay? So looking at these functions, so if you go to the spectrum, this is just GLN over GLN is, so taking the prime spectrum, this is just taking dn over Sn, and this is a finite group, and this is an affine space. So this is what we know for matrices, right? And then saying that you have a Chevalier restriction theorem means that if you have a polar representation of a group G, you want to be able to play a similar game. So what you will have is that if you want to study the ring of regular functions on your representations that are G invariant, there will be a small, smaller subspace of V such that this ring of functions is the same as taking the ring of function on this smaller subspace. In our case, it was diagonal matrices before, under the action of a finite group. And again, so again, in all this situation, passing to the spectrum, this is telling you that this quotient is the quotient of on a fine space by a finite group, and in fact, this group will be nice enough so that this is an affine space. It's a pseudo reflection group. Okay, so polar representations are representations for which this holds.
It's not always symplectic, right? The affine space.
Not that I know. Not.
Like in general, you make it symplectic or homoric, you have to put extra conditions.
Yes, I think so. I mean, there is work of Boulois, Len, and Terperot who were studying a symplectic version of this theorem, but they need to add extra conditions. And they have, in certain conditions, under certain conditions, they have an isomorphism, but not for all situations. Okay. So,
the Shipley restriction theorem is usually just for the non-symplectic case. I don't know.
I mean, Chevalier restriction theorem is here, and yeah, you don't have a you're not considering symplectic, but you can take, say, you can take V plus its dual and have a, say, for the adjoint representation you have a symplectic version of it, but for general polar representations there is research going on, but not, yeah. What is
I just didn't know about this. I haven't heard about such a theorem for symplectic case.
It's a commuting parameter, right? So if you want to take C plus its dual,
yes,
take a commuting parameter like that.
yes, exactly.
Not improved for general to that definition type A.
I'm not sure what the question is.
I don't know what the statement is. It's okay.
So the statement here is you have this isomorphism.
Yeah, I know this statement, but there was this talk about the symplectic version.
Oh, this, yeah, in that case you would have, you take V plus its dual, right? And
right, exactly. So then you were saying that for the other position, then we know what we get, but that's in the type A case, right? Or we take the reduced.
well, yeah, you would have, like, I mean, this would be the adjoint representation.
For type A, in general type, I think it's no, that's we take the reduced part.
Yeah, okay, the reduced part. Okay. Yeah, probably, yeah.
Is it obvious what C is in each of these two versions of E? Is it obvious what your space C is?
Yeah, now I'm going to test. Okay. So they are polar, as I said, and what you have here is so we would like to see what are the spaces C and in these two representations, and in general you have this, say, when you're talking about matrices, you have this dichotomy that elements are can be split into a sum of some part that is diagonalizable and some part that is nilpotent. And so essentially what you want to know here is what is the nilpotent part. The fact is that for the enhanced module, this is observed by Springer, is that if you want to know what these functions are, well, these are essentially, these are exactly the same functions that you would have on GLN. You have nothing more, essentially, because you see you have the diagonal matrices acting on here, and you have no invariant. There is no hope you can get any invariant out of this function. Okay, so So this is precisely as before. And I write C as a field, but if K would be also, any K would do. Okay, so in the case of the enhanced module, C is just diagonal matrices. Okay, and in order to explain what the space C for the exotic module would be, I would like to give you another interpretation of this module. So, a different look. And so, consider GL2N. So it's just 2n by 2n matrices and the adjoint action on it. And then this decomposes as a representation of SP2n as SP2n, the adjoint, plus something else. And this something else is precisely this module.
There's an additional trivial.
What?
There's an additional trivial.
Yes, you're right. Okay. Okay. So, no, there is not.
No.
There's not.
Let's say there's not. The GL is.
I mean, the trivial is inside here.
Oh, it's inside here.
It's inside here. Okay, so this part is what we have over here. So the exotic module for SP is again can be seen as a module of matrices plus a vector part. Okay, so these are precisely, if I want to see them as endomorphisms, that are the self-adjoint endomorphisms with respect to the symplectic form I have here. If you want to think of it in terms of matrices, for instance, for the form, or the symplectic form with this ground matrix, then this guy is something like A transpose B, C, where B and C are skew-symmetric. Okay. I mean, this is one option. So if you look at it in this way, then it's quite so it's over here. Again, if I want to look at invariant functions on E, certainly these parts will be trivial again, because again you have the diagonal matrices of SP acting here, and there is no way you can build say a non-trivial invariant function on this vector part. And here you have matrices, and so what happens is that this is the same as taking oops, I should choose SP2n, and this is just taking the diagonal matrices on here, but you see this is A, and here you have its transpose, so in fact what matters is only this part.
You change K6 or
Yeah, okay. Let's say KC, but it really works also for any odd characteristic. But let me write C. Yeah, maybe I should explain. The reason why I use C is that the theory of Dado and Katz the paper is only about C. But the results that we are using for these modules are there in any case. So, okay, and this is, therefore, just taking again the diagonal matrices n by n, and then for the symplectic group, for the symmetric group. So the quotient is the same of these two modules. So I want to describe it. I would like to describe a little bit the relations between these two modules. Say putting together some of the results of several people. So relations between E and
just so I can understand that, so you're saying that if you look at this alternating space, the diagonal matrices are paired across the anti-diagonal, they're totally written as
they're here. You see, okay, it depends on which form you take, but if you take this one, then you say to describe a diagonal matrix, you only
The biogroup plus Peter is bigger, but this big part acts trivially, so you're only interested in symmetrical.
exactly. Okay, so the only action that survives is this one.
So if instead of E and epsilon, you also pick SO n with symmetric group, and that one, are you going to put that similar?
We didn't try. We are focusing on this. Some things can be said in general for polar representations, but we have quite specific questions for these modules for several, yeah. I can imagine that certain things can be generalized. But there is something very special about this module. For instance, now I want to describe certain things. So I guess you are familiar, but I just repeat it with this notation. Suppose you have a group, I don't know, H1, which is a subgroup of H2, and H2 acts on some variety Y, then I can construct the product H2 times Y, and H1 acts on it by this action, acts freely. You're not happy?
You start with Y with an action of H2 or with an action of?
I'd like to have an action of the bigger group. And then what you, this action is free, so you can take the quotient and no, it doesn't matter. And you call it the associated bond. Okay, and the action map gives you a map to Y. Okay, so you have H2Y goes to H2Y. This is why I wanted the action of the bigger group. So you have this associated bundle in general, and what is nice is what is at least of interest to us, is that essentially the geometry that you have over here can be carried over the. Should I repeat some? I mean, I know that people have different notations for this construction.
And the H2 star Y is the equivalent class. So it's the image.
Yes, this is a class in this portion, so I don't know. Yeah, class of H2Y. And I will usually, when I construct a gadget like this, I will usually call this map by mu or something. Okay, so you can construct this bundle for SP. And in fact, I could take here the exotic. I take here, well, so my Y is E, and I can. You're right. You're right. I should have taken a smaller one, but okay. I can construct this bundle. In fact, for this, as Daniel was pointing out, it's enough the action to be of H1. And then here, this goes to H2 to Y. It's not very nice, but
okay, but Y was included in something where H2 acts.
exactly. So Y H2 acts on some X which contains Y. So yeah, probably this is what I should have said. Okay, so H1 acts on Y and H2 acts on some space which contains Y, and then this makes sense. Okay. I'm sorry. Okay, then with this identification, if you keep this in mind and you keep also SP2N as contained in GL2N, you have this inclusion of GLN into GL2N, and you get also automatically an inclusion of the enhanced in the exotic. So maybe I can write it over here. So the inclusion of GLN into SP is just as a Levy subgroup. So if you want to have some GLN inside SP to N, which is having an element to depends on the form, but it's this one, and then SP2N is contained in GL2N by whatever. It's clear how this is contained in the other. And again, the enhanced representation can be seen inside the exotic by, well, you have a matrix and you have a vector. You have a matrix A and a vector B, and this goes in this way. So you can, so this will be my Y, and this will be my X. Okay, so this goes to, so the action map will be going to E, and it's a result of cathode, and this is surjective. So to answer, it's not obvious how you find two things that are paired like this. And if you go to the quotient, as we observed, what you have is that if you go over to the quotient here, if I call this E twiddle, then E twiddle over SP2N, as a matter of fact, whenever you have this this bundle here, you have an action of the bigger group from the left, which is free. So you can take again the quotient here. You can take the spec of the invariant functions for H2, and this is the same as taking the quotient of Y for the action of H1. Of course, everything must be nice, but in this situation, the groups and the representations are nice. So this is the same. This is always the case, is equal to E over GLN. And if I go over here, this is E over SP2N. And as we have seen in the example, it was observed by Springer, these two things are equal. So the picture you have is that these modules are related in this nice way. And and there is pretty much more to this. And this is why I think this is interesting for symplectic singularities, even if we didn't prove anything about it. But so you can look in here at what are the nilpotent cones. So nilpotent cone would be the fiber of 0 of this map here, and the fiber of 0 of this map here. So the set of points for which the invariant functions are triggered. So you have the nilpotent cone of the enhanced. So I call this map pi the twiddle, and call this map pi of V. This is pi of V twiddle, the fiber of 0. And since, and by what we have seen, this is precisely the nilpotent cone of GLM plus the vectors. And the nilpotent cone of the exotic is pi over is the fiber at 0. And from what we have seen, this is the nilpotent cone of self-adjoint operators plus, oops, I'm switching the field all the time, to plus this.
So I'm sorry, the statement of the equality, is it just a statement that you can check that the map induced by the...
I mean, this is the definition.
No, above the previous word, this equal sign, is it saying that the map you get from the top induces an isomorphism?
Is really the idea, essentially the idea is the isomorphism of taking a diagonal matrix and doubling it. It's an isomorphism.
You have a specific isomorphism in mind between those two.
Yes.
And the curly E over SP.
Yes, you have a specific isomorphism, which comes from this, the inclusion you have made of E into say enhanced into exotic, and
but it's not obvious up here that's an isomorphism, right? Just because you computed both sides.
yeah, if you want, I mean, you have both sides, and the rings are really the same. And
Then you can check that the diagram also convinces.
but I mean, this is really, I mean, if you look at Springer's paper, it's really explicit. I mean, it's really telling you, well, if I have a self-adjoint operator, what matters is only the upper there, and then I'm looking at the regular functions are precisely the coefficients of the characteristic polynomial of this block, and so on. So, I mean, it's really okay. And now you have these nilpotent cones, and another important result is that this is not true for every polar representations, but the number of nilpotent orbits, so the number of orbits for GLN here and the number of orbits for SP here are both finite and can be parameterized. So you can consider this. I want to count the set of orbits. Well, this is in bijection with bipartitions of n. And partitions means that they are a sequence of non-negative numbers, negative integers going down, both mu and nu, and their sum is n. And the funny thing is that this is the same parameterizing sp2n. The sp2n orbits in the exotic cone. So they are parameterized by the same objects. And the bijection is simply you have an element A and you double it and put 0 here, and for the vector you put 0 below. So if you have a representative of an orbit here, in here it will be represented by, you have a matrix and a vector, you have.
I'm a little bit confused there because the E tilde, the source of that is the E tilde. It looks to me like when you take pi E tilde and this is really going to be in bold E. The first line of the scoring here.
The first line, yes?
Pi E tilde, source of that map is E tilde.
Yeah, but then I look at it in E. So.
Then it's a different map. Not pi E tilde.
Okay.
I mean,
Okay, so. Okay, but they are in bijection, and the interesting thing is that they are not only two sets that are in bijection with the same combinatorial elements, but the bijection is a coset bijection. So it means that when you study closures, an orbit, say the bijection preserves the closure conclusions. And the dimensions are doubled. So it means that if I have an orbit here corresponding to mu nu in the enhanced cone, then its dimension double is the dimension of mu nu in the enhanced. So the questions, this is a result by Achar and Henderson. Lift it up. This is a result by Achar and Henderson, and is obtained by direct calculations, both the closure inclusion and the dimension property. But say we really think that there is something here. I mean, we expect that these orbits are symplectic and that these things are Lagrangian in there, but we couldn't prove it yet. Okay, so So I mean, there must be a reason for these properties. And we believe that understanding the geometry of this picture is the answer to this. Will help us to understand why you have this property, why you have this.
Is there a minimum? I can't remember there must be a partial order of these partitions. So is there a minimum?
I don't think so. Let me see. I can show you. For instance, if you do the simplest example, if you do the simplest example, that is for n equal to 2, then you have the orbit corresponding to 2, 0, which is represented by this one. And then this goes down to 1, 1, which is represented by 0, 1, 0, 0, 1, 0. And then you go down in 2 different ways. So this is and then you have the trivial one. Yeah, the trivial. So it doesn't look like you have a minimum. The point is that, you see, the thing that starts with a 0 vector can only close 2 things with 0 vectors. So somehow these things, you have the minimal over here, yeah.
But the minimal on the left, the closure is probably C2. So it's what's the orbit closure?
The minimal
On the left. So the other one. On the left.
Yes.
The vector. So the orbit closure, I guess it's a 0 matrix and any vector.
Yes,
so
exactly.
That's C2, so this one is.
Mm-hmm. No, I mean, yeah. So if you take them separately, then you know everything that is essentially going on. But the problem is to understand how they interact. Okay. So, yeah, okay. So this is one of the reasons why we got interested in that. We would like to understand better what is going on. And there are open questions about this also. Whether, say, which closures are normal, and
Do you have information about
no, I mean, no, you have, what you have is the results of Achar and Anderson and results of Kato, who describe essentially a resolution of the cone, and Achar Anderson also have resolutions of all the closures of orbits. And then they describe local intersection cohomology, and they have a conjecture that also at the level of intersection cohomology, you should have a doubling phenomenon that say the things that occur. I mean, you have non-trivial cohomology only in even degrees for the enhanced, and you expect that you have only in multiples of 4 degrees for the exotic. But I mean, this is a conjecture they made. I looked it up, and it doesn't seem that anybody picked it up. Okay.
Can you just explain how you get from the two partitions representative? So it's not the
Yes, I can tell you. So how you do that is, suppose if we write it this way, you can think of it like taking two boxes on one side, and then you look at here, and these two are giving you a Jordan, say a basis for the Jordan vector. So it means that x, the operator is mapping this to this and then to 0. Like this is giving you a Jordan block. So if you take row by row, this will give you the Jordan form of your element. And then this is telling you at which spot, say which, where to put the 1, essentially. So if you have, say, how much you can go left with your vector here before it's killed. Okay, so, and I mean, it's a little bit of work to show that in fact you can get two things that are decreasing, and that this is unique.
So if you remove the bar, you just get the normal partition of the Jordan block.
So if you, I mean, if you had a partition like this, then yeah, you would have to remove the bar to have the Jordan form.
The 1, has a Jordan block of size 2, you said.
No, this means you have the partition so, and the bar here. And 0, 0.
The one above it, the 1 bar 1. The 1 bar 1 above it. That one you said the Jordan block of size 2 also.
Yes.
Oh, right.
It's good.
Yes, it's right. It's right because you have the bar and you have 1, 1. So you have to add them side by side. So if you had something like 3, 2, 5, 7, your partition, this is no good, 5, 3, then your partition would be 3, 5, 3 plus 5, the first one, and 2 plus 3, the second one.
Yes, it's not removing the bar, it's adding a.
Yeah, it's removing the bars once you write it down as with boxes.
So you put the V immediately on the left of the.
Yes, exactly, here. And then you look at here, and it's the sum of what you find here. I mean, you don't see it here because it's too small, but otherwise, your vector would be a sum of terms.
This is for
the enhanced.
The bold D.
And then you double it, and you let the symplectic group act. And it's a theorem that, in fact, all are represented by this. I mean, it's not obvious.
Since you double the matrix, and for the vector, you just leave it the same.
Yes.
And then the enhanced, the exotic, the curly is called exotic.
Yes.
And that one is a symplectic singularity.
One expects it to be. One expects it to be. I mean, so the questions is in general the closure of an exotic orbit, a symplectic singularity, and in particular the closure of there is a regular one, so there is no minimum, but there is a maximal one. The closure of the maximal is the code, is the Nilpotent.
Do you have a Poisson structure on the
It's not obvious. Is not. Say one of the tricky things is that if you can try to make this into a Lie algebra, it's not really a Lie algebra. It's more like a symmetric Lie algebra. But then it's not obvious that it's isomorphic to its dual. So yeah. Say finding you cannot use the usual trick because G and G star are not isomorphic. But
this could be odd dimension. This could be odd dimension, right? So,
no.
So lambda 2.
I mean, I'm sorry. Yes. Yes. Sorry, I was thinking of the Nilpotent. The Nilpotent is always even dimensional. But the whole module,
the Poisson structure like a singularity on that.
What we were trying to look at is more like looking at the structure for GL2N and then trying to do a Hamiltonian reduction, but at the moment, I mean, we really didn't think enough about it. I cannot tell that it's difficult, it's simply we didn't do our homework enough. Okay, but maybe it's time to start thinking about what we did. So to go back to the question of this morning and the fact that just to make a connection, the fact that sheets are interesting objects. What we were also interested in were indeed decomposition classes and sheets in this setup. So let me recall what the Jordan certification is. So this is a stratification you usually have on an adjoint representation of a reductively algebra. This was introduced by Borrow and Kraft when they wanted to introduce sheets. But the group version was introduced essentially at the same time by Lustig when he described generalized Springer correspondence. And it's a way to stratify an adjoint, say, a Lie algebra or a group according to the Jordan decomposition. So essentially, what it is the typical example I make is what somebody teaching linear algebra has to do when he's setting up an exam. So you start with your you start with choosing an exercise in which you want to your student to find the Jordan normal form of some matrix, and suppose you choose this one, and then you conjugate. But then you have a lot of students, and the room is crowded, and you want to make different exams, but then you want to be fair. So what you do is you change slightly the eigenvalues, but keep the Jordan form essentially the same. So you can take 5, 5, 1, 1. So what you're doing is you're keeping the discrete data, that is the algebraic multiplicity and the geometric multiplicity, but you change the continuous data, namely the eigenvalues. And in this way, say you are creating equivalence classes of objects that have the same nilpotent part and the semi-simple part with the same algebraic multiplicity. Okay? So let us now give the formal definition. So if I have two matrices, X will have a semi-simple part, so a diagonalizable part and an nilpotent part, and Y, another matrix, will also have a semi-simple part and an nilpotent part, and I say that they are equivalent if the stabilizer, so the set of matrices that commute with XS and YS are conjugate, so if there exists a G in GLN such that G, the centralizer of XS, G inverse, is the centralizer of YS, and the centralizer is precisely the centralizer of this part is just giving me the algebraic multiplicity. So telling that they are conjugate is essentially telling me that they, that the algebraic multiplicities are the same, and I want the nilpotent part to be the same up to conjugation. Okay, so whenever I choose my two matrices in this way, I'm being fair with my students. Okay? So this is an equivalence class and an equivalence relation on GLN, but I can do it on any algebra. Whenever I have a decomposition of a semi-simple and a nilpotent one. And the equivalence classes are called decomposition classes or Jordan classes or packets or so one can do this game. No? You have.
I was wondering. Okay, once you know that you have the same centralizer,
In fact, these two, or in general, I mean, in fact, for GLN, this means exactly that the two matrices have the same centralizer to work. For groups, it's more tricky. But if that was.
I was wondering something, but never mind.
Okay, so if you forget about that we were talking about GLN, you can take a G and D of G. And repeat the same thing when G is a reductive group. And so what we know about Jordan classes is that Jordan classes are finitely many. They are locally closed, so they have a nice geometric structure. They are irreducible. They're smooth. The closure of a Jordan class is a union of Jordan classes. They are clearly G invariant by construction. They are unions of orbits of the same dimension.
It's not the same, it's just saying that the centralizers of X and Y are quantity.
In this case, it's true. In GLN, it's true. And in fact, in a Lie algebra, it's true. So you can, so for any reductive Lie algebra, this is the case. I mean, it's not obvious to prove, but it's not super hard either. And in fact, one can describe the closure. One can describe the closure in terms of induced orbits. So the one has an explicit description of the closure. And in particular, when you take the closure of a Jordan class and you intersect it with the important cone of the Lie algebra, this is the closure of a unique orbit. And you can take, say, a nice, and this worksheet that occurred this morning is always described as the closure of a Jordan class, say a maximal one with respect to, say, inclusion and staying in the same level set. So for instance, this is one of the reasons why Anne Moreau was interested in closures of Jordan classes and their singularities. And another thing that is nice about Jordan classes is that when you want to study them locally, they say any neighborhood of a Jordan class essentially looks like the neighborhood of an nilpotent orbit on a smaller group. Okay. Essentially, you reduce to looking at what happens in the centralizer of the semi-simple part. So this is so it's a nice stratification we are really interested in because it has been useful in many occasions, and it thickens a bit the nilpotent orbit stratification, because when you if this group here is SLN and you start with a nilpotent element, so this part is not there, then what you get is precisely a nilpotent orbit. So so you're thickening the space on which you're studying, and you're thickening the stratification. And when you restrict to the nilpotent cone, you get the stratification of the nilpotent cone in terms of nilpotent orbits themselves. Okay, so the point is that this was something one would do on a Lie algebra, but you can do it again on the exotic and enhanced Nil code. So you can repeat it. So you can construct a Jordan stratification on E and B. Because what are the ingredients? The ingredients are, on the one hand, having a Jordan decomposition, and on the other hand, it's more hidden. You need it more in the proofs of these things rather than in their statements. You need the Chevalier restriction theorem. I mean, you need some invariant theory. Okay, so you have the ingredients. You have the ingredients because if you have an element, say, in both these situations, what we had observed is that the enhanced was GLN plus some vectors, and this was self-adjoint operators, so operators plus some vectors. So in both cases, your module is of the form some matrices plus some vectors. And we know that the nilpotent part in both cases, so this E is either this or this, was the nilpotent of the matrices plus all the vectors. So we know what a nilpotent element is. A nilpotent element is one inside here. And what is a semi-simple element? Well, these are the elements corresponding to closed orbits. So you simply take the semi-simple elements inside the matrix part. So the elements, semi-simple in M. And this is really easy to see because they are described in terms of matrices. So you know what a semi-simple matrix is. So we know what these elements are. And for this reason, any element E lying in an enhanced or exotic module will be of the form x times b, where b is a vector, x is a matrix, and so I can decompose it in this way, and I can repeat a similar equivalence relation. So I can say my element E is XB, my element X is YW, and the semi-simple part of X, of E, will be the semi-simple part of X, and the nilpotent part of E will be the nilpotent part of X B, and again, the same for Fs. And the equivalence relation is simply saying they are equivalent if there is an element in G, and G is GLN in one case, SP in the other, such that G, ES, G and the stabilizer of ES is the stabilizer of SS, and G acting on En is Fn. And this is again an equivalence relation, is well placed, and again you can define the equivalence classes. Which we call again Jordan classes. And what we could prove is that they are finitely many, they are locally closed, they are smooth, their closure is a union of classes. By definition, they're union of orbits of the same dimension. We don't have an explicit description of the closure, we have a conjectural description of the closure. The only annoying part is that we couldn't prove yet that this intersection is irreducible, so we cannot say that. I mean, we have a conjecture. Say once we prove that this is irreducible, we know which closure is. We know the what. So we still miss this point, but we are positive that this will work out. And in fact, the other thing is that thickening this stratification thickens also the result of Achar and Henderson, namely first of all, say there is a one-to-one bijection between Jordan classes in E and Jordan classes in the exotic module. And we expect, but we didn't finish the proof, it relies on that point that it's a bijection of posets. Say the closure we expect that this holds, so that this picture is like, yeah, thickening all the results by Achar and Henderson. But
Is there a partition?
yes.
The same?
Is there a partition trick? You mean?
Yeah, partition description of the poset.
Yes, so what you need to do is essentially when you take a semi-simple element, the stabilizer in the exotic is a product of symplectic groups, and so you're reducing to say a bunch of new exotic, smaller exotic cones. So you take, maybe I can draw a picture. So if you have a semi-simple element and you take it diagonal, then the stabilizer will be some sort of product of symplectic. Now I'm making only two in this way. And the nilpotent part will be in the enhanced cone of this symplectic, in the exotic cone of this symplectic times this symplectic. And then you can reduce. So when you want to parameterize, you have to say what partition is giving you the product of the symplectic, and then a bipartition for each of these parts. And you have a picture of how closures should behave, but they are only conjectural. I mean, and also we have in the adjoint case, what this orbit is a very well-known and interesting object related to Springer representations, that is the induced orbit, and it corresponds nicely to inducing representations via the Springer correspondence. And we have, and say this conjectural orbit is obtained by taking the induced in the adjoint part and choosing the maximal vector you can put there. But yeah, it's just a conjecture. Okay, so yeah, I think I finished early.
Thank you very much. We finished right on time, but we have a few minutes for questions.
So in the case of just taking over the adjoint representation of any simple Lie algebra, then there's a lot of interest in these transverse solid slices, which you could construct just given an SL2 triple. Do you have something analogous, but say a Nilpotent orbit, classification of Nilpotent orbits? Do you have some sort of obvious trace of a transverse slice or something equivalent to?
In fact, that is the problem. That is the problem we have with the construction. The fact that we would like, say, the reason why we couldn't prove this is that we couldn't find an optimal character. So your H in the SL2 triple, say if you're able to find the H for the SL2 triple, essentially you're able to find something decent as an optimal character. And this is the thing that I'm sure that, say, if one understands this one, say, then as a cascade gets everything essentially for free. There is, in the paper of Kato, he constructs a semi-simple element associated to an nilpotent element, but it doesn't do exactly what we want it to do, but almost, so maybe that is the right thing.
So the ultimate goal would be something like a sort of practical Chasey set of analysis of the local geometry of each orbit closure using some equivalency.
Yeah, or at least understanding, what kind of singularities, at least as a global thing. I mean, like a Panishev type of theorem. I mean, the being able to say the closures are normal, it seems to be tricky enough. But I mean, for instance, from the point of view of symplectic singularity, you could have, so you expect maybe to prove that normalization of the closure is a symplectic singularity, and you could do that even if you don't know if the closure is normal. You have a general statement. But yeah, maybe that would be useful.
You expect these to be normal, would you say?
All of them?
I mean,
There is some, the fact that they are really close to type AN and to, and the fact that the nilpotent cone is normal. The whole cone is
right,
normal.
but
The closure of the orbits,
surely you don't expect them all to be normal in the exotic case.
I
There should
don't
be isn't there a relationship, some kind of relationship with the nilpotent cone for XO2n, because
it's,
sometimes you project that
yeah,
there you have non-normal.
this object is somehow, on the one hand, it has very type C from the point of combinatorics, but from the point of geometry is more close to type A, in the sense that, for instance, the Springer correspondence is a bijection. So, say it's a funny thing. So you might, it could be that it's simpler from the geometric point of view than the type C itself. But for instance, the stabilizers are connected, which is not the case in general.
What's the Springer correspondence here? Are you talking about the Jordan classes?
No, the Springer correspondence is resolved by Kato, and it really associates to each nilpotent orbit, so to each bipartition, a representation of the Weyl group, type C. So it's not the Weyl group of the exotic, which is Sn, but really the Weyl group of the symplectic group. And the bijection, he does it with Borel-Moore homology and with evolution. Not with
So you said
projection.
that the Springer correspondence was like type A.
In the sense that there are no non-trivial systems.
Ah, I see. That's
Because the stabilizers are connected, so you.
And also that it's a bijection.
Yes.
So you said that the conjecture that they're in this setting, in this exotic setting, conjecture that you actually get a single orbit closure in the set.
Yeah, we expect to get a single orbit closure, but we did examples only in very small dimensions, so it's not.
And it works in that
Essentially, we expect.
enhanced case.
The proof. If one proves it for one proves it for the other. They are really say it. Yeah.
Isn't there an obvious closure relationship between these Jordan classes if you just look at the matrices and the vectors? So
one inclusion of closures is obvious and the other is not. You have.
You could have some additional things in the boundary which are obviously so.
Yeah, but even one can describe the exotic. I didn't tell it, but in terms of symmetrically algebras. But even in that case, so if there are examples of things you can construct that are stable for an involution and for which the closure relation is not just taking the fixed point for the involution. Also for certain quiver representations. And so, there are some. I don't expect this to occur in this case, but to exclude them with a proof is another thing. Okay, I'm sorry.
Maybe we can continue after. So let's thank Giovanna again. So we still have the little decision for what we do with the So yeah, you said you would. I would write with you the lesson. Yeah, do you have any open problems that someone